Although the universe is vast beyond imagination, the laws governing its workings are elegant and concise. For instance, all interactions can be attributed to four fundamental forces that control interactions across different scales: gravity, electromagnetism, strong and weak forces. These shape the entire workings of the universe. What do we know about them? Gravity is the most familiar force, as we feel the Earth's pull constantly. Newton first described it mathematically, proposing that objects with mass exert gravity, and that it has infinite range. However, he did not explain how it arises. In the 20th century, Einstein's general relativity conceived gravity as warped spacetime around matter. This curvature in turn guides motion. However, gravity's particle form remains a mystery. It awaits quantization. Though physicists predict a graviton particle, its existence is unproven. Among the four forces, gravity is the feeblest. A small magnet can lift a paperclip off the ground, overpowering the entire Earth's gravitational pull. Yet gravity alone attracts indefinitely across space, hence accumulating immensely. Thus, it dominates the macro scale governing celestial motions. Electromagnetism denotes interactions between charged particles, currents, and magnetic fields. Its polarity allows diverse structural forms. Atoms have positive nuclei and negative electrons, while molecules bond electromagnetically. Electricity and magnetism were thought separate, until the 18th century showed their likely unification. Changing magnetic fields induce currents and vice versa. Maxwell unified them mathematically as electromagnetism. Later, quantum mechanics conceived the photon as electromagnetism's quantum. Photons transmit electromagnetic forces. In daily life, forces like friction and elasticity manifest electromagnetism. The strong force acts only microscopically, binding quarks into hadrons like neutrons and protons. Its residual effect also sticks protons and neutrons into nuclei. Its discovery came when particle accelerators collided particles with nuclei, producing short-lived particles besides protons and neutrons, inferred as quarks bound by a new force. There are 6 quark flavors: up, down, strange, charm, bottom, and top, and 3 colors: red, green, and blue. Quarks interact by exchanging gluons. The strong force grows with distance but weakens at proximity due to asymptotic freedom. Separating quarks requires vast energy input, but before quarks fully separate, enough energy already exists to produce new quark pairs. These quickly repair with the old quarks, yielding 2 hadron pairs. Thus, quarks remain confined in 2s and 3s as mesons and baryons, like 2 quark pions and 3 quark protons. The strong force is the mightiest among the 4, powering fusion in stars. The weak interaction was uncovered when some radioactive elements spontaneously emitted electrons or positrons. This beta decay was traced to a new fundamental force, the weak interaction. It also acts only microscopically, mediated by W and Z bosons. It changes quark flavors, transforming particles. For instance, it can turn a neutron's down quark into an up quark, emitting a W boson. The W boson rapidly decays into an electron and antineutrino. Neutron beta decay into a proton. Conversely, it can change a proton's up quark into a down quark, decaying into a neutron by positron emission. Importantly, the weak force's matter-antimatter asymmetry enabled the universe's evolution post-Big Bang. It also facilitates hydrogen fusion, transforming 2 protons into a deuterium nucleus by the weak interaction. In summary, this outlines the 4 fundamental forces concisely. Details and open questions remain to be explored. That concludes today's overview. Please stay tuned for more.